She had a really impressive CV. She had good grades. She'd taken some time off. She'd gone to a Peace Corps. She was currently in Costa Rica where she was working with sea turtles. So I was really impressed with her CV. And so we worked to try to figure out, okay, she's in Costa Rica. She doesn't have the best computer access. How can we Skype? But we did finally find time to Skype. And that's actually where I got my first maybe a little bit of concern whether she could do the lab. Well, either way, I'm sure you guys all know this. There's definitely a theme of I like turtles. I had never worked with turtles, so I was a little hesitant about, okay, she really seems to have this focus on turtles. I'm excited about that. But what we decided the best approach would be is maybe she should come out to the lab, figure out if she wanted to work with me, or kind of if I thought I could mentor someone that wanted to work with turtles. So she came out for an intro. Oh, see, now let's see if I can actually get to go to this slide. So she came out for her intern year, and while she was an intern, she decided she would take a class. One of the things she said she was a little nervous about is after time away from school, how did the classwork go? I have to admit, I was a little concerned when I walked into the lab. She might be using a little bit of alcohol to get through some of her assignments, but she definitely seemed to result in some. But somehow she managed to get one of the best grades in the class. She had strong academics, so wanted to see how she was in the field. She was great out with the elephant skills, but when we did some of the boat work, she really tried to hide it during these early years. Like to actually look at her face. Probably really focusing on trying not to throw up. But what really sold me on the fact that she'd be a good fit for the lab was how she embraced the stranding program. She was willing to go out. This was, I think, one of her and Jenny's adventures. There was a dead whale in Big Sur, and they just took off with some knives. Collected some samples. She always seemed to have a smile. Like, having someone that's willing to climb on dead things is mean. Despite having no bullying, like, I heard she was the worst of her team. But still participates. And then just in general, we just wanted to thank you for all your hard work, helping everyone else. And there does seem to be a theme in how she smiles. Photos like this. With that, I would like to just share it and hope you guys enjoy her talk.
All right. Well, thanks, Geeta, for the wonderful introduction. That was pretty spot on. And thank you, everybody, for coming today. I'm actually really excited to talk to you guys about my thesis, which is titled Using Stable Isotopes to Determine Foraging Areas of Leatherback Turtles and Limitations of the Isotope Tracking Technique in the Western Atlantic Ocean. So I guess we'll just jump right in. The big question of my thesis is actually, does foraging in different areas result in differences in reproductive output? So we know that reproductive output has long been linked to foraging area quality, and that individuals foraging in high quality habitats with high resource availability will typically have better body conditions, higher survival rates, as well as greater reproductive output. And this can essentially just be defined as bigger, better, or more babies. So then if we have a population where certain individuals are predictably foraging in one area while others are foraging in a different area, are some of them going to predictably have bigger or more babies? And why does this really matter? Well, I think we're all familiar with the concept of shifting baselines and the idea that what we see as pristine and natural now really wasn't the case 10, 20, or hundreds of years ago. And we know that human actions are changing marine environments. It's a fact. So the question that comes up is, how do we assess potential consequences of these changing foraging grounds? And I guess the answer is, one way is to understand animal movements and the processes that drive them. So we need to be able to track them through these foraging grounds. And how do we do that? Well, since the technological era, one of the primary tools for tracking long-distance movements of aquatic animals has been satellite telemetry, which essentially just consists of attaching an electronic tag to an animal that can record various data types ranging from simple presence and location to really extensive time series records of the animal's movements and environment. So if you look at this photo here, all of these animals are wearing an electronic satellite tag. And these tags are able to collect data that help researchers produce maps like this one, which actually traces individual leatherback migrations through the North Atlantic. There is a drawback to satellite telemetry, however, which is that tags are really, really expensive. So this typically results in limited sample sizes for a population unless you have a ton of money to get a ton of tags. So in order to study the movements of a larger number of individuals in a population, researchers have been increasingly using stable isotope analysis as a lower cost complement to satellite telemetry. So now is the question, what is stable isotope analysis? Well, for me, it's easier to understand if I break it down into these four concepts. Number one, biologically active elements exist in different forms. So let's take carbon, for example. Most of the carbon in the world exists as carbon-12, but there's about 1% in the world that exists as carbon-13, and the only difference is just the number of neutrons. Number two, local ratios, and also keep in mind as we're talking about stable isotopes, the values are essentially the ratio of heavier to lighter isotopes, and this is measured against international standards. So local ratios are going to vary, and they're altered by different biogeophysical processes in the areas that we find these stable isotopes. So as another example, the local processes that govern carbon isotopes here in Monterey Bay are going to be different from the processes that govern isotope values in Cape Cod. And we expect that those values will be different. Number 3, consumer tissues integrate values from their local food webs. So this is essentially covered by the saying, you are what and where you eat. So you can expect that if you have a consumer foraging here in Monterey Bay, it's taking up all the carbon isotopes from Monterey Bay, and these values are going to be different than a consumer that's foraging off of Cape Cod, taking up all the values coming in from Cape Cod. And number 4, we have prior knowledge of spatial variations of these stable isotopes. So we need to know how stable isotopes differ in Monterey Bay versus Cape Cod, for example. And this is where I'll introduce the term isoscapes. So isoscapes is pretty much like an isotopic landscape. It's like having a map of stable isotope values. And this is just one that I want to show you. For example, this is a carbon isoscape made from phytoplankton in surface waters. And you can see how there's different values associated with all these different regions. So to sum it up in a very hypothetical and simplified concept, stable isotope analysis is based on the idea that stable isotope values in different environments are governed by local biogeochemical processes, and that consumer tissues are integrating this information from their local food webs. And lastly, that we'll be able to pick out these differences using stable isotope analysis. And just keep in mind, please, that this is extremely simplified, and in the real world, it is much more complicated than this. Isotope values are highly influenced by temporal variations as well as changes through trophic levels and even the specific tissue sampled. But let's move on, and I'll introduce you now to the 2 stable isotopes that we'll be talking about in this study. So we'll be focusing on carbon and nitrogen. And you'll be seeing both of them in a scatter plot like this, with carbon along the x-axis and nitrogen along the y. And you'll notice that both of them are denoted with the delta symbol, which is just expressing that it's a ratio of heavier to lighter isotopes. So for delta carbon-13, it's going to be the measure of carbon-13 to carbon-12. And for the rest of my talk, I'll just be referring to it as carbon. And then for delta nitrogen-15, it's the measure of nitrogen-15 to nitrogen-14, and I'll just be referring to it as nitrogen throughout the rest of my talk. So why these elements in particular, and what can we tell from carbon and nitrogen? Well, in marine systems, carbon values are typically driven by temperature and dissolved organic carbon. Spatial differences in isotope values can differentiate between inshore versus offshore regions and benthic versus pelagic areas. And typically, nearshore systems with greater nutrient concentrations and productivity are less depleted, meaning they have higher values when compared to offshore and pelagic systems. So values also typically tend to decrease with increasing latitude, like you can see in this map. And local values are reflected in the base of the food web in things such as algae, phytoplankton, and particulate organic matter. And these are integrated into consumer tissues. So working backwards, if we're looking at spatial variations or just variations in carbon of higher order consumers, we can typically infer nutrient origins. So nitrogen in marine systems is typically determined by the dominant nitrogen cycling regime, and areas associated with greater nitrogen fixation are associated with lower nitrogen values, while denitrification is associated with higher nitrogen values. And generally, nitrogen is used more in diet studies to look at diet composition and trophic levels, and greater values are associated with higher trophic levels due to enrichment in consumer tissues. So again, local values are reflected in the base of the food web and then integrated into consumer tissues. So both of these elements together have been used to infer movements in foraging regions of highly migratory species, which is actually what we'll be focusing on today. So I just want to briefly touch back on our big picture question. Does foraging in different areas result in differences in reproductive output? If we have a population where certain individuals are foraging in one area and others are going to another area, will some of them predictably have more, bigger, or better babies? And now for the fun part. We get to talk about turtles. So, although the big picture question is applicable to any species that has inter-individual specializations in foraging areas, I'm going to present leatherbacks as our ideal species for using stable isotope analysis to identify foraging regions. Leatherbacks are the largest of all turtles, and adults can grow up to 2 meters, and that's just their shell length. So you can see in this picture on the left, we actually have our very own Scott Benson sitting next to an adult female turtle, and I believe this one was about 180-something centimeters. Leatherbacks have existed in their current form since the age of the dinosaurs, but recent stock assessments show that nearly all populations are declining, mainly as a result of human actions. So the current biggest threats to leatherbacks are being caught as bycatch in fishing gear, egg and meat harvesting, and nesting beach habitat loss and pollution. So I guess for conservation purposes, it really is critical for us to understand their movements in at-sea ranges. And they are our ideal species for using stable isotope analysis to identify foraging regions because of 3 reasons. Number 1, they eat gelatinous zooplankton. So leatherbacks essentially all feed on the same trophic level. They're all eating things such as jellyfish and pyrosomes that essentially are composed of seawater and have isotope values derived from very baseline local influences. As a result, leatherback tissues are incorporating all of these local values from the areas that they're foraging. Number 2, they express fidelity to foraging areas, so their isotope values are in theory reflective of months of foraging in the same area. And leatherbacks are known for really long migrations between both nesting beaches and foraging areas, and they also express site fidelity, so they go to these same areas over and over. And this map actually shows the migration routes of 3 turtles from the same nesting beach in Panama, going up to their respective foraging grounds. And this is just half of their migration. So the other half will be when they return back to Panama to lay their eggs again. And a typical adult female will make this remigration every 2 to 3 years. And the last reason that leatherbacks are an ideal species is that they're really easy to access and sample, at least once they're on land. So when females come on land to nest, they're pretty awkward, they don't move fast, and then once they actually begin nesting, they go into what we call a nesting trance, where they're just busy putting out their eggs, and they're pretty oblivious to anything else that's going on around them. So you can see in these photos, you have Scott on the left, and then Desi on the right, who was actually another Moss Landing grad, and they're both working with nesting turtles during the nesting trance, and the turtles probably have no idea what's happening. All right, so it used to be believed that leatherback populations in the Atlantic were doing well relative to the Pacific population, but most recent stock assessments show that nearly all Atlantic populations are also in decline. So this subpopulation in the Atlantic is actually divided into 7 rookeries, and you can see all of them here. They're color-coded by nesting location on this map, and we'll be focusing specifically on the Western Caribbean rookery, which is here. So females from this rookery actually nest from Honduras to Colombia, with Caribbean Costa Rica being one of their nesting strongholds, and that's where we'll be focusing on today. So after nesting, previous studies with satellite tracking data show that females from the Western Caribbean rookery will forage in at least 2 different regions, and one of them is the Gulf of Mexico. The other is in the Western North Atlantic. And so these 2 tracks that you're looking at here are from actively transmitting leatherbacks that were tagged in Panama. And you can see on the left, this female is swimming around in the Gulf of Mexico, while the one on the right is swimming around in the Western North Atlantic. So focusing specifically on these foraging areas, the Gulf of Mexico is considered the least productive. But based on genetic analyses, up to 43% of the turtles found in the Gulf of Mexico do come from Costa Rica, so we know it's an important area for them. And this could be because of the warmer climate, which can reduce metabolic costs, and also the proximity to their nesting grounds, which can provide another energetic advantage over other regions. So typical round-trip migration between their nesting grounds in the Gulf of Mexico is less than 5,000 kilometers when compared to the North Atlantic, which can be actually over 10,000 kilometers. And so relatively, the North Atlantic is much further, and it's characterized by colder water with greater productivity and denser food supplies. So despite this greater travel distance from their nesting areas, leatherbacks, only larger leatherbacks have the increased thermoregulatory and metabolic abilities that allow them to access these colder waters. And these larger turtles typically have larger energy stores, and they're able to lay more eggs. So now we're beginning to see a little bit how foraging region might actually impact reproductive output. All right, so to recap a little bit, thus far we've established that females from the Western Caribbean rookery use the Gulf of Mexico and the Western North Atlantic for foraging, but what we don't know yet is the extent to which the population uses these foraging areas and how each area might actually impact their reproductive output. So in order to address these questions, my thesis has 3 objectives. Number 1, use stable isotope analysis to measure skin, carbon, and nitrogen of leatherbacks nesting in Costa Rica. And this is essentially, we need to determine who's foraging where. And I hypothesize here that values will reflect foraging regions used prior to nesting. Number 2, we want to assess differences of foraging region on female body size and reproductive output. So here I hypothesize that females foraging in the North Atlantic will have a greater body size and have greater reproductive output. And lastly, we want to review existing stable isotope literature to create isoscapes for the Gulf of Mexico and for the Western North Atlantic. This is because I wasn't able to buy satellite tags to definitively link isotope values to specific foraging locations. So this really was just my attempt to create a map of reference values for each of these locations. And as I mentioned earlier, since stable isotope values are subject to temporal fluctuations and changes between trophic levels and tissues sampled, here this is just my attempt to find as much data as possible from as many different taxa as possible to create a reference to use. And I hypothesize that spatial patterns in stable isotope values will be conserved from lower order to higher order consumers in both regions. All right. So moving on to our methods. Remember, we're focusing on the Western Caribbean regional subpopulation here. And this research is going to take us to Caribbean Costa Rica, specifically to a very remote site called Parismina. It's a village of about 500 people here. And although there are so few people, it's actually one of the larger nesting grounds for leatherbacks in Costa Rica. And in past years, it's had over 200 turtles in just one nesting season. So the nesting beach spans 6 kilometers from, in the north, the mouth of the Rio Parismina, all the way south to the Pucquar River. And essentially what I did was I packed up everything I needed for 5 months and took a plane, 2 buses, and a boat to Parismina for the 2018 leatherback nesting season, which lasted from March through August. And I was working together with ASTOP, which is a local conservation organization based in Parismina. And every night during those months, we patrolled the beach in rain, in mosquitoes, in heat, in sinking sand. And patrols were done from 8 p.m. to midnight or from midnight to 4 a.m. And I took a skin sample from every turtle that we observed either before or during the nesting trance. So I chose to sample skin because turtle skin has a slow turnover rate on the order of 4 to 6 months, and it's been shown to hold isotopic signatures for up to several months. So to take skin samples, let me refer you to this photo on the left here. All we did was take a pair of forceps and pinch a little bit of extra skin from the rear hind flipper, and with just a standard razor blade, we just cut right underneath the forceps and came away with a tiny skin sample, which I preserved immediately in 70% ethanol and froze as soon as possible. Over the course of the season, we identified 60 individual turtles, and I was able to sample 31. And I could only sample 31 because the other turtles we observed after their nesting trance, and at that point, we don't want to disturb or handle them. And so taking that into consideration, we still did sample over 50% of the nesting population that season. So for these 31 turtles, I also took body size measurements using a flexible tape measure, similar to what Desi's doing here in this photo. Body size measurements for this study were curved carapace length, which is the length from the tip of the middle bony ridge to the tip of the carapace, shown here in red. And also the curved carapace width, which is the curved distance from the widest part of the carapace from one side to the other, shown here in blue. Leatherbacks are known to nest multiple times in a season, and so I attempted to collect reproductive output from each female during her first nesting bout whenever possible, just to standardize our data. I collected clutch size, which is literally just the number of eggs, egg mass and diameter, and I did this for 15 randomly selected eggs per clutch to get an average value per clutch. And it typically takes leatherback nests about 60 days to incubate, so after about a couple months, I had hatchlings to work with. And I measured hatchling mass and body size, and once again, this was done for between 1 to 15 hatchlings per clutch to get an average value per clutch. Skin samples were processed and prepared at NOAA's Southwest Fisheries Science Center in La Jolla. Samples were dried and diced with the razor blade, and lipids were removed using petroleum ether. And all the prep samples were sent off for analysis to the light stable isotope lab at the University of Florida. And remember, I also wanted to create isoscapes. So to create isoscapes, I searched for stable isotope data from previously published studies, and I combined all the results together to develop regional carbon and nitrogen isoscapes for the Gulf of Mexico and for the Western North Atlantic. And of all of the resulting literature, there were only 5 taxa that I could find that had isotope data available for both regions. So my isoscapes included particulate organic matter, zooplankton, jellyfish, loggerheads, and leatherbacks. And I just acquaint yourselves with these images because they'll be popping up again later. And I found a total of 10 published papers and 2 unpublished data sets from collaborating researchers. And now we'll move on to the results. So average adult female curved carapace width was 111.52 centimeters, and curved carapace length was 153.16 centimeters. So I'll give you guys just a second to process that. These leatherbacks, and the measurements are just for their shells, are measuring over 1 meter by 1.5 meters. So these are very large animals. And these sizes were actually pretty comparable to other populations. So usually leatherbacks reach maturity at about 145 centimeters, though in the Atlantic some have been shown to reach maturity at smaller sizes, which we also found in this population. So you can see my smallest female was 135 centimeters. Average clutch size was 76 eggs. Average egg mass per clutch was 81.66 grams. Average egg diameter was 5.2 centimeters. So just to give you guys a ballpark, leatherback eggs are like this big. And unfortunately, only 19 of 31 clutches hatched. This is actually pretty normal for leatherbacks. They have a really, really poor hatching success, and to have a nest hatch with a 30% success rate is pretty good. So of these 19 clutches, I ended up weighing 214 hatchlings and also did body size for them. So mean hatchling mass per clutch was 47.1 grams, and mean hatchling curved carapace width was 4.05 centimeters. Curved carapace length was 5.91 centimeters. So again, we're going from these tiny baby hatchlings that are, about this big to animals that are over 1 meter by 1.5 meters. And now you guys can see like why I find leatherback so interesting. Like just think about the energy that takes to go through this exponential growth. All right, so for stable isotope analysis, leatherback skin samples had carbon values ranging from negative 18.17 to negative 15.39 parts per mil, and nitrogen values ranging from 9.1 to 13.97 parts per mil. So here again, you can see our scatter plot, and all of these values are the individual values from the 31 turtles in Parismena. And what I want to point out here is there is no clear clustering of values by foraging region. It just looks like a mess. But the one thing that does stand out here, and that we'll come back to later on in the discussion, is the wide ranges that we see in our values. So just keep that in the back of your mind. Okay, and because carbon's generally used to look at locations such as near shore versus offshore, I used carbon as a potential indicator of foraging region, and I used linear regressions to test the relationships between carbon and, in slide A, adult curved carapace length and curved carapace width, in B, average hatchling, curved carapace length and curved carapace width, average egg mass and hatchling mass, average egg diameter, and also clutch size. And essentially, I mean, you guys can see here, I found no relationship between carbon and any of these body size measurements or reproductive output. So moving on to the isoscapes we created as a reference map, I want to first orient you with what we'll be looking at over the next few slides. So each isoscape is going to display a different taxa, and you can tell what it is by the image and the text in the upper left-hand corner. So this is a carbon isoscape for leatherback turtles. The shaded regions on the maps here are going to, they're going to represent areas where data were available, and the regions are color-coded using shades of green for low values and moving to red for higher values. And the general regions we'll be covering are Canada and Nova Scotia, up in this area, Massachusetts, South Atlantic Bight here, which actually spans North Carolina to Florida, the northern Gulf of Mexico, and the western Gulf of Mexico. And there's also a few regions in the Caribbean, but I'll define those as we get to them. So looking at our carbon isoscapes for all 5 taxa together, we found that the lowest carbon value was negative 23.4 parts per mil, and this was found in particulate organic matter in the West Florida shelf. The highest was 10.5 parts per mil, and this was found in loggerheads from the Bahamas and Cuba. So in these carbon isoscapes, there really were very few consistent trends among taxa and sampling regions. So in other words, regions with the lowest and highest stable isotope values really varied between taxa. And I'll show you one example, which is the northern Gulf of Mexico was a region of very low carbon for zooplankton and loggerheads. But at the same time, it was a region of very high carbon for jellyfish and leatherbacks. So remember that carbon generally tells us about locations such as inshore versus offshore and benthic versus pelagic. And we also generally expect these values to be transferred up the food web. So to have the northern Gulf of Mexico be a region of both low and high values for these different taxa was really unexpected. We found similar trends in nitrogen. So again, each of these maps represents sampling regions for our 5 taxa. The color-coded bar moves from low values in green to high values in red. And here we found that the lowest nitrogen value was 2.0 parts per mil. This was found in zooplankton in the western Gulf of Mexico. And the highest was 12.9 parts per mil. This was found in loggerhead skin from the northern Gulf of Mexico. So like I mentioned, here again we found a similar trend to carbon where there's just a lot of variation among taxa and sampling regions and just very little consistency. So for another example, the South Atlantic Bight was a region of very low nitrogen for jellyfish, but of very high nitrogen for loggerheads and leatherbacks. So remember that nitrogen generally tells us about trophic levels and the dominant nitrogen cycling regime in the area. And we also expect these values to be transferred up the food web. So to have the South Atlantic Bight be, once again, a region of both low and high values for different taxa was not expected. We did find some notable results, though, which is that the northern Gulf of Mexico had the greatest nitrogen values for 3 of our 5 taxa. And this was for zooplankton, jellyfish, and loggerheads. And leatherbacks. And the western Gulf of Mexico had the lowest values, but data here were only available for zooplankton. So all that being said, I was unable to use these isoscapes as a reference to determine foraging area for the Parismena turtles. But if we focus specifically on leatherback data, we do find that average carbon value is significantly greater in the Gulf of Mexico when compared with the Northwest Atlantic. And this is determined based on 95% confidence intervals. So there is a possibility that our turtles from Parismena with the highest carbon values are coming from the Gulf of Mexico. And now we'll move through the discussion, but I'd like to break it back down by objectives and kind of retouch what we're looking at. So objective 1, remember, was to use stable isotope analysis to measure skin carbon and nitrogen of leatherbacks nesting in Costa Rica. Number 2, we wanted to assess the differences of foraging region on female body size and reproductive output. And number 3, we wanted to review existing stable isotope literature to create isoscapes for the Gulf of Mexico and the North Atlantic. So looking at objective 1, I hypothesized here that stable carbon and nitrogen isotope values would reflect prior foraging region used. They didn't. So there really weren't any distinct clusters, and I wasn't able to use stable isotope analysis as a primary tool for determining foraging region. However, we did see some very interesting things. So the range in nitrogen values of the turtles in Parismena is really interesting. Their range was 4.8 parts per mil. And there is a generally accepted rule that nitrogen increases by 3.4 parts per mil for every trophic level. I say this is generally accepted because, once again, this is subject to variation between organisms and tissue sampled. So, however, this is a generally accepted rule, so if we apply this, the observed range in our Parismena turtles might indicate that these leatherbacks are foraging over at least 3 different trophic levels. So we might envision some sort of food chain like this, where Parismena turtles with the lowest nitrogen values are feeding at 1 trophic level, and the other ones with the highest nitrogen values are feeding at a higher trophic level. However, we know this is highly unlikely because leatherbacks all have a very generalized feeding strategy on gelatinous zooplankton. So instead, the range in these nitrogen values actually suggests that there is some spatial variability in nitrogen values across the different foraging areas accessed by these turtles. And this kind of brings us back to this really simplified scenario of spatial variation of nitrogen values that are conserved up through the food web. And moving on to carbon, carbon appeared to be a much better indicator of foraging region because we were able to pinpoint the Gulf of Mexico as a source of high carbon values. And this was, once again, based on 95% confidence intervals. So we also saw a very wide range of carbon from leatherback sampled in Parismena. And if we were to superimpose mean values measured from the northern Gulf of Mexico, Canada, Massachusetts, and the South Atlantic Bight, we would see something like this. So each of these color-coded boxes are the average values found in each of these locations. And we already know, based on satellite telemetry, that Western Caribbean leatherbacks forage in the Gulf of Mexico and Canada. So if we were to further superimpose the actual values of the 95% confidence intervals for each of these locations, we would see something like this. And the interesting thing here is that most individuals from Parismena are falling between Canada and the northern Gulf of Mexico. And the logical assumption is that they're coming from these locations. However, without satellite telemetry to back us up, we really can't confidently say that this is what's happening. Which leads us to conclude for objective 1 that we need satellite telemetry. And then moving on to objective 2, remember we wanted to assess the differences of foraging region on female body size and reproductive output. And what I had hypothesized was something like this. So I hypothesized that leatherbacks migrating longer distances to forage in the cold but highly productive North Atlantic would have a greater body size than females that were foraging in the warmer but nutrient-poor Gulf of Mexico. And as a result of greater body size, that females foraging in the North Atlantic were going to have greater reproductive output. But unfortunately, we ran into a couple issues. The results of this objective really depended on being able to determine prior foraging region, which we weren't able to do. And as a follow-up, when I compared carbon values as a proxy for foraging region to body size and reproductive output, I really found that there was no relationship between carbon and any of these measured parameters. So for objective 2, unfortunately, I didn't find support for my hypothesis that body size and reproductive output would be influenced by foraging region. But this does contrast many previous studies that have linked the two. So one possible factor that may have influenced my results actually involves reproductive output measurements. Reproductive output can commonly be quantified through a whole list of parameters, and for leatherbacks and sea turtles in general, these include clutch size, clutch frequency, fecundity, egg size, egg mass, hatchling size, hatchling mass, hatching success, emergence success, and remigration interval of the adult turtles. And this study really only measured 5 parameters of reproductive output, and it was only done for one nesting season, and these parameters are shown here with asterisks. So I do think that with an increased sample size and longer-term data collection, and also measurements of other parameters here, that relationships between foraging area, body size, and reproductive output may be detected. So unfortunately for my project, a lot of these other parameters are really difficult to come by and do require really intensive and long-term monitoring. So as an example, I had access to data dating all the way back to 2012. But even with all of this data, I could only pick out fewer than 10 individuals that nested enough times for me to determine their remigration interval. And although we patrolled the beach every night, the beach did span 6 kilometers, so as we were at one end of the beach, we were missing turtles that were coming up at the other end. And so we still missed individual nesters, and with this, we weren't able to determine other parameters such as clutch frequency. So concluding objective 2, we definitely should have increased parameters measured and also have longer-term data collection. Moving on to our third objective, we wanted to conduct a comprehensive review of existing stable isotope data to create carbon and nitrogen isoscapes for the Gulf of Mexico and Western North Atlantic. So here, remember, I hypothesized that there would be distinct spatial variability, and that spatial patterns in baseline producers would also be similar in higher order consumers from the same regions, and that I would be able to use these isoscapes to match Parismena leatherback values to their respective foraging regions. Again, this wasn't the case. So in creating these isoscapes, I found that there really isn't enough data. So compiling literature results really doesn't take into account temporal and spatial variations. Looking at all of these different studies, there wasn't a standard sampling time, and some studies may have been affected by things like runoff or anthropogenic influences. So this really just resulted in a lot of inconsistency, and this might actually be further complicated by looking at so many different taxa. So there was some good stuff, though, that I found, which was that there is a general latitudinal gradient of decreasing carbon values with increasing latitude, and this does support previous literature. And I also found that predator and prey isoscapes, meaning leatherbacks and jellyfish in our case, were pretty similar. So for future use, it might actually just be best to focus on predator and prey isoscapes. So concluding our third objective, existing isoscapes would definitely benefit from more data. So as an overall wrap-up, although we weren't able to use stable isotope analysis as our primary technique to determine foraging areas of leatherbacks, this study did report some of the first stable isotope values for the Western Caribbean population. And it also set up some very basic predator and prey isoscapes for the Gulf of Mexico and the Western North Atlantic. So I do think that this project would have been much better supported with satellite tracking, and that might actually be a worthwhile pursuit for future grad students. And we'll always benefit from more published isotope data. And I also do think that stable isotope analysis still has really great value for conservation and for tracking, but because there is so much fluctuation and variability, once again, it does need to go hand in hand with satellite telemetry. So I guess with that, I'd like to thank everybody that has helped and supported me through the last, 3.5, 4 years now. So to my committee, Geeta, Jim, Jeff, you guys have been amazing. I actually have a really cool story about my committee that I'm not sure all of you guys know. But the formation of my committee started a long time ago. Back in 2012, I was working for Fish and Wildlife in La Jolla, and we were sharing a building with NOAA, and that's where Jeff works. I was getting ready to go to Costa Rica to work with turtles, and somebody told me, hey, you should really talk to this guy named Jeff. He's like the turtle expert. So I ended up sending this guy named Jeff an email, and I was like, hey, I don't know you, but I'm going to Costa Rica. Like, can you give me some insight? He was super nice, and he responded, and we chatted a little bit. Then I left. And then in 2014, this is like 2 years later, I'm living in Costa Rica, still working with turtles, and thinking about going back to grad school. And I was like, where do I start? And in the back of my mind, I remembered, hey, there was this guy named Jeff that I talked to a long time ago. Maybe he'll talk to me again. So out of the blue, I sent him an email. I was like, hey, you don't remember me, but we talked a couple years ago. I want to go back to grad school. Do you have any insight for me? Not only did he have insight for me, but we ended up having like a full-on Skype conversation, and he sent me a long list of schools and researchers to look at for when I wanted to go back to school. So that was really amazing, and I started looking through the list, and this guy named Jim Harvey popped up, and Moss Landing Marine Labs popped up. So I was like, oh, I'll check this out, and I'm like looking through it, and I was like, this sounds really cool. This sounds like the place that I want to be at. So then I emailed Jim. Jim passed me off to Geeta, and then Geeta just finished the story at the beginning of my talk. And so now, like 5 years later, I'm standing here, and I have all three of you. And I never would have expected that. So thank you guys for being so awesome. And Geeta, you are so loved by all your students. Thank you for always looking out for us and making sure we're doing okay. And always looking to keep us funded and, you know, make sure that we've got roofs over our head. Or tables. Jim, thank you for always being the realist in my committee and asking all the hard questions and for making me figure out most of the answers that I could figure out on my own. And Jeff, thank you so much for always being so accessible. I think you guys have spoiled me in terms of like what I expect for response times in emails. Because usually now if you guys don't respond in like 2 hours, I'm like, okay, like what's going on? And Jeff, thank you for being so open and just so positive all the time. You know, I never would have anticipated that. And you have a way of talking to people that you just make them feel like they've done something amazing, even if they've just like fallen on their face. So thank you for that. And I want to thank everybody that helped me in Costa Rica. I won't go through the list, but I do have very good stories of them if you guys are interested afterwards. And I want to thank the folks at Southwest Fisheries Science Center, Garrett for showing me around the lab and essentially babysitting me for 3 days as I processed my samples. Aaron for helping me transport my samples. This was a whole fiasco, and I ended up having to leave my samples for a month in Costa Rica, and Erin dealt with it like a boss. She just She was so patient and calm over email. She walked me through everything I had to do to get my samples back, and for that I am forever grateful. For Scott Benson, who showed me essentially how to take skin samples from leatherbacks and has always been so positive and encouraging. And also Karen Forney, who just will talk to me about leatherbacks all day long. Like, she's been really encouraging as well. And for Moss Landing Marine Labs, I don't even know where to begin. Like, we all know we're a community here, and there's been a few people that have really stood out to me in my time here. So I do want to give a special thanks to Tara, to Michelle, to Katie, and to Kenneth. They've really been awesome. You know, they're the people that make me happy to be here, because when I see them, they say, hello, how are you doing? Like, how can I help you? What do you need? And they really make me feel valued. So thank you guys so much for that. And then James is also on this list because I don't know if you guys know this, but James has an eye out on all the students, and he's like your go-to guy. So for example, he probably knows what car every one of you is driving. And if you were to maybe accidentally rear-end somebody and come to school with a dented bumper, he would probably come to your lab and find you and ask you if you're okay. And also, if he were to find out that you may or may not be sleeping under a table in the lab, he would also come find you and ask you if you were okay and if you needed anything, and he would tell you to move your car from the parking lot to the courtyard because he didn't want it up there. So James has your back, you guys. And for the Vert Lab, I'm going to hold off on this because I have a whole nother slide for you guys. For my funding sources, for the H.T. Harvey Memorial Scholarship, Viola Palmer Memorial Scholarship, Myers Trust, San Jose Graduate Equity Fellowship, MLML Scholarship, San Jose State Archimedes Scholarship. I couldn't have done it without these sources of funding, so it's been really amazing to have that. And also for people who donated. I sent out a call for donations before I left for Costa Rica because Paris Mena really is an impoverished community. And for as hard as they try to keep their conservation project going, they never have enough supplies. So before I left, I sent out an email asking people to donate headlamps because that's what they needed the most when I went. And so Holly, Kathleen, Chris, Alex, and Kate, you guys all donated things, and it really did make all the difference that year. So thank you so much. And lastly, okay, so this is the Vert Lab. I love you guys, and when we talk about community, like, this is what I think about. I sent out a very last-minute email because I wanted to have my practice talk on a Sunday evening, and this is like the week before finals, so everybody should theoretically be super busy. But guess what? Almost everybody came, and everybody stayed for over 2 hours to listen to my talk and then give me feedback. And this is the kind of support I think about when I think about the Moss Landing community. Because not only did they come in for me on a Sunday night, the next morning at 8 a.m. before classes, they all showed up again to listen to Bree's talk. And so, like, it's been amazing to have this support for the last 3.5, 4 years. So thank you guys so much. And lastly, I do want to talk about this little ray of sunshine here. So Jenny, I love you. I met this girl my very first day interning here, and I had no idea what was in store for me, and we ended up dragging a 200-pound dead harbor seal up Spanish Bay, and I think that was the moment that I decided you were going to be my friend. So you've been there for me for the past 4 years, and I think a lot of you know this past year has been pretty tough for me, like on a personal level. And the number of times that I've showed up at this girl's house, sometimes in the middle of the night, just because I needed like an emotionally safe place to stay, has been pretty ridiculous. But she never made me feel that way. She always had her door open, and I didn't know this kind of empathy existed. So Jenny, thank you so much for that. I don't think I could have done this without you. And I guess after that, I'll now take any questions.
they might be high. And so, one thing is trophic level, but we found that, there are other things that can elevate or enrich nitrogen 15. So did you think about some of the other possible enrichment
I did.
tracks? And
Yeah. So I know for leatherbacks, nitrogen was super high as well in the Gulf of Mexico. And one thing that's really impacting that area is stuff like runoff and anthropogenic influences, pollution. And so I did take that into consideration when I thought about like high levels of nitrogen. But yeah, the Gulf of Mexico was my main focus in terms of like looking at nitrogen. So yeah.
Can I suggest one?
Yeah.
And I have no idea if this will apply, but for sponges we think it may is starvation and also.
Oh, yes. So, okay. I guess this goes into a whole nother thing, but there has been some debate on whether or not fasting will increase nitrogen levels in different animals. And in reptiles, most studies show that it doesn't, at least not in their tissues, but in their excrement it does. And so for my specific project, I didn't talk about this in my presentation, but I did resample 3 turtles. And I looked at nitrogen and carbon and how they changed over time. I had the span of 2 months in between first and second sampling. And actually, their nitrogen values didn't change. So it kind of supports the idea that reptiles don't, even if they're fasting, because leatherbacks are fasting, the values aren't going to change very much. But once again, it was only 3 samples, so yeah. Ryan.
Sorry, Gary, did the turtles switch between those foraging areas and on what time scale?
Yeah, so typically they have a general fidelity to their specific foraging area. So those that go to the Gulf of Mexico will most likely go back to the Gulf of Mexico, and those going to the Atlantic will probably keep using those areas. But it's a little complicated because where they go specifically in those areas can change, so as they're going up through the North Atlantic, like if they're feeding at all, they could be taking in all these isotope values as they go up and come back down. So, yeah.
If you were to go out and get your perfect isoscape map, where would you like to direct someone to go with an isoscape map?
I actually really want to focus on the western Gulf of Mexico because there was very little data there. I think one of the reasons is because it's hard to get permitting to work in that area. So the only thing I could find from that area was zooplankton, and that was just based on one study done like in the 80s. So if I had a chance to go back, that's where I would want to focus. Yeah. Yes, Sophie.
Do you think that you would have found that this technique would have been useful if you had sampled multiple types of tissues? I know that you're dealing with live animals, so you're not going to...
Yeah. I mean, maybe, but we chose skin based on the turnover rate, and because leatherbacks aren't foraging as they're nesting, we wanted it to reflect as far back as possible. So if we had chosen something else like blood, it might just be turning over too quickly for us to get any signals out of it. But it would still be interesting to look at all of that. Yeah. Yes, Brian.
Excellent job.
Thank you.
I'm really interested in the apparent contradiction between the levels of carbon versus the levels of carbon in turtles versus the level of carbon in their. So I'm wondering if perhaps the Nova Scotia jellies were individually higher in carbon, but lower in population than the Gulf of Mexico jellies, and so even though they were getting a lower quality food, they were able to eat more of it?
It's possible, but I don't, and maybe I'm not understanding exactly the question, but theoretically, like if you're just eating a certain thing, no matter like the quantity of it, if that's the basis of your diet, you should be incorporating all those values. Mm-hmm. So even if they're not eating as much in a certain area, but that's all they're eating, that should probably still be reflected in their tissues. So did that answer? Mm-hmm. Okay. Yep. Anybody else? Am I off the hook?